Hello and welcome back to Quantum Computation Explained Part 2. So in this video we are going to see how two numbers can be added using a quantum computer, of course a quantum simulator. Um, you may be surprised, just for addition of two numbers do we need a quantum computer? Yeah, certainly not only for addition, but then the purpose of this video is to highlight how rotational gates can be used for addition, and then how QFT is used for addition. And in the process, we will learn a lot actually about quantum computation. So that is the purpose of this video. So we all know that arithmetic operations can be done, in fact have to be done in a quantum computer, then only it will become useful. Since we are talking, we are in the early stage of quantum computing, both software and hardware, we have to do a lot for adding two numbers. I mean, it's a good thing that to learn how two numbers are getting added in a very, very basic state. Of course, after few maybe months or years, we don't do this kind of operation because there will be a built-in function. There's a nice software to handle like what is being done today, because we really do not know how two numbers are added inside, are added or multiplied inside a computer, right? Classical computer, we just make one simple statement and we get the answer. So same thing will happen here, but we need to know what is happening in the background, and also we can see whether it can be improved in terms of execution, in terms of number of qubits or memory and things like that. So we are going to see two different types of quantum addition in this presentation. So before going to quantum addition, let's see how classical addition is done. Again, we'll try to have a quick recap. I'm sure you are all familiar. So it's done with full adder circuit with the XOR and OR gates, as you can see here. So let's say that, let's say we have three bits. You know that every given number should be converted to binary. And then addition is done with respect to each bit, and there is something called carry forward. So carry in comes from the previous bit addition, and similarly this addition will give out carry out, which can be used for the next bit addition, and the answer is given set in this bit. So this is the truth table. Again, you are familiar. Let's see, when all the bits are 0, you will see the sum also 0 and carry out also 0. So when sum will be set, so when any one of them become 1, sum alone will be set, like 0 0 1, 0 1 0, 1 0 0. So when carry bit will be set, so carry bit will be set when more than one of these three bits is set. For example, B and carry in is set here, A and carry in is set here, A and B are set here. So at that time you will get 1 1 in carry out. And when all three are set, what happens? So 1 plus 1 plus 1, 3. Okay, so 3 is binary form, 1 and 1. Both sum and carry out will be set here. Okay, this we are familiar. The question is, can you do a similar way in a quantum computer? The answer is no, you are familiar. The reason is these gates cannot be used in quantum computer. The reason, these gates cannot be represented by unitary matrices and they are not reversible. There's another point in quantum computer, the number of input should be same as the number of outputs. Of course, that is not a big deal, but that is one more point we need to remember. So this cannot be used, right? So we need to see how to do the addition. So addition is done through C0 and CC0 gates. So I'm sure you are familiar with that. If you are not, please go through my previous videos, quantum computation simplified, particularly at part 1 to 5. So if measurement is done, and then some qubit and carry out qubits are set here. So in this case, this is sum and this is carry out. So like the previous classical case, here we have A, B and C in. Okay. So this is set when any one of them are not one, one or three of them are set. So for in this case, when we want to add 1 and 0, and you are familiar, right? When we in qubit, quantum computer, initially all the qubits will be in 0 state. So if you want to represent 1, you have to use a NOT gate. So now 1 will flip this guy. So from 0 to 1 it will become, so answer will become 1. In case these two bits are also set, then they will get a flip from 1 to 0, again it will become 1. And when carry bit will be set, this is an interesting thing, please note that. So that will check the combinations of 2 from 3. So what are the combinations? We have A and B, B and C, A and C. Okay, A and B, A and C, B and C. When any of these combinations are set, then carry out will be set. Okay. So this is something similar to what we have seen in classical addition, but using different gates, correct? So we will run it in a simulator. Okay, so this circuit I have already made so that we save some time. So here I am trying to represent a number using 2 qubits, unlike in the previous slide where we had one bit for each number. So here we have 2 qubits for A, 2 qubits for B, and the answer we will have in these 2 qubits, but the carry forward and that is set in this qubit. So 3 qubits we are interested in, 2 for the sum and 1 for carry forward. Okay, so let's start. As you can see here, that we use only control not or control not, CC not. So initially all qubits are in 0 state, answer is also in 0 state. So now let's change it to 1. So 1, this is set here. Now the answer is also 1. Now let me set this guy. So answer should be 2. 2 is represented by 1 0, correct? So 1 0. Now let me change this to 2. Sorry, 1. When I make this as 1, then it will become 3. Number 3 plus 1, 4. So at that time what happens? 4 is represented by what? 1 0 0. So this 2 will become 0 0 and this will become 1. So shall I do that? Okay, we got it, right? So again we'll add 3 3. Okay, what happens? 3 3 is 6. 6 is represented by 1 1 0. Correct? Very simple. Exactly the same way like what classical computation is done, but we have a different set of gates. Alright, so what's the drawback of this method? The drawback is we need more number of qubits. We need at least 3 times n qubits to add 2 n-bit numbers. And this is not an efficient way because we are already running sort of a number of useful qubits, logical qubits, correct? So again, people have thought about it, they come out with nice algorithms and they try to do with less number of qubits. So that is done with the help of quantum Fourier transform. I don't know who is the real inventor of this, but there are many references available. I have given some of them at the end of this presentation. So in this method, we are trying to reduce the number of qubits by removing the temporary and carry bits. And another major advantage is it supports parallelization, which will reduce the speed. So this is an important point. Okay, so we will see how parallelization can be done once we make the circuit. So now I'll go back to, okay, let me go to Qiskit, but this time I'm not going to IBM experience. So instead, IBM has given another way for us to do. We don't have to go to that cloud computing. We can do it in our computer itself. So I've set an environment such that the Jupyter notebook itself available in this computer. We can access quantum simulator or quantum computer of IBM's. So again, I already made the file. Okay, so this cell, standard, we are trying to import all the library functions, except this is a new one which I have not used earlier. So here I am trying to use the built-in QFT function. So this is a function which will help us to change the given numbers, two numbers, to qubit state. Okay, so this is an important step. So whenever you want to represent numbers, you can use this kind of function. So first this two is a good Python statement which will help us to create a binary string for each number. So we have to define how many bits of binary string we want to use. So here I am declaring 3b, and in case the number is lower than that, it has to pad that number with zeros. For example, if I have a as 1, so it has to say 001 binary string. Okay, this it has to create a string and assign it to a bin and b bin. And this next steps are all for building the quantum circuits. So as I told you, we are going to work with a smaller number. Say let's have 3 qubits for each number. So for A 3 qubits, B 3 qubits, and each one we are giving it representing in a different register. So we'll call it as A register, B register, and then we need one classical register to tap the state of qubit, and finally that will help us to get the answer. Then here we are building the circuit with these three registers. And this one important step we have to see because as I told you earlier, whenever we start the qubits are in zero state or low energy state. So if we want to represent 1, we have to convert that 0 state to one state, right? I'm sorry. So that is what is being done here for both number A and B. So this 2 minus I is a little bit confusing, but don't worry. So that is to make use of the IBM's convention of the least significant qubit is the first qubit. Okay, so for that reason we are having this 2 minus I index. Otherwise it is just making the state of a qubit as 1 whenever the binary string is 1. Okay, and that is done with the help of a NOT gate. Okay, so that just flips from 0 to 1. And this is the important function which actually does the addition by rotating. Okay, this you will be surprised, right? So, but it is an interesting thing. That's why, in fact, I released this video mainly. You get a better understanding of what's happening. How to manipulate the qubit. So, we are doing some controlled rotation. CP is nothing but rotation. With respect to z-axis. So we have to define what is the control register, what is the target register, and how many qubits we are having, and that has to be done on this circuit. So we'll understand you will understand it better when you see the circuit. So I'll not spend much time on this to explain. So this is the main function. So wherein let's start with a equal to 2, b equal to 3, and then n, the number of qubits what we have as an answer will be 3. So we are converting number 2 and 3 and drawing the circuit of QC. Then as I told you, we are making use of the QFT function to convert the state of qubits, which from measurement basis, that is 0 and 1, to some Fourier basis, which will be in terms of some angles. Okay, so again I also need to understand this function a little more, because some people use 2 1 0, but I'm getting answer only when I put 0 1 2, and then swap. If you put true, again there are some issues. I'm using false. Okay, so now I'm after representing the qubit states, then we are converting to Fourier basis. Then the addition takes place by rotation. So again here we will be calling this function many number of times, and inside again we'll do many number of times as given here by both for loops. So don't worry, we will explain, I will explain with the circuit. Then once the addition is done, we need to get back our numbers in terms of measurement basis, right? Then only we'll know what number it is. So that is done by calling inverse function, inverse QFT. So okay, so here QFT, here QFT dot inverse we are calling. Otherwise other parameters are same. Afterwards we try to measure the QA or A register. So you might have noticed the answer is set in A register. Okay, because okay, let's see the circuit. So both A and B numbers are converted to quantum states. Okay, then we are doing QFT on A register alone. You can do it on B also, it doesn't matter. So generally it is done on the larger numbers. Okay, then this is what is the important thing. So what the function what we have written does is, it takes the corresponding bits, for example the most significant bit to most significant bit of the other number. So when this is control rotation, so whenever this is set, this will rotate the state of this qubit by pi radians. Similarly, based on the state of the second significant bit, it rotates again the same most significant bit by pi by 2. This is something like carry forward, okay, in a classical method of addition, or the previous method what we saw. So like that, depending on the number of qubits, we have to go, will be doing the control rotation like pi by 4, pi by 8, pi by 16, pi by 32, like that. We may stop in between if we know, if we are happy with the accuracy. Otherwise, this is the approach which will be followed. So that is done to get what is the value of this qubit. And now how this, because this is going to have the answer, right? So how the second qubit is set. So that is set with the help of the second and first. Okay. So whenever second is set, you will do pi rotation, and whenever the next bit is set, you will do pi by 2 rotation. So now 2 bits we have done the addition, and the last one is least significant bit to least significant. So here, so there is nothing carry forward coming from the other qubits. Okay, very simple way of adding numbers. Then we need to convert to by measurement basis or 0 and 1 format. Afterwards we are making a measurement and we are going to get the answer. What is the number we have set here? 2 and 3. 2 and 3 is, answer is 5. 5 is 101. Okay, 101. And interestingly, it will, the probability of getting 101 is 1. That is something great, right? But that greatness will go off instead of using a simulator if you use the actual quantum computer. but certainly this will have higher probability. So instead of 5 having 1, it will have maybe 7.7, and other 3, 4, 6 also may come, of course, depending on the type of qubits used, type of gates used, and of course the time of execution. Okay, so they all will determine the probability, but certainly this will have a highest probability. But luckily we don't have that noise problem, so we are able to get one probability. So shall we add one more number? Maybe I'll make it 1 and 2. So answer should be 3. Okay, so before that I need to execute all these cells. Done. Now let us see the circuit. 1 and 2 is there or not? Okay, so 0, 0, 1 is 1, 0, 1, 0 is 1. So the answer should be 3. 3 is 0, 1, 1. Correct? So let me run it. 0, 1, 1. Great. Okay. So like this you can try out a different thing. I'll try to share the code. So the important takeaway is we are adding by rotating. That is a great thing, right? So this really, I'm sure, will kindle your mind, and then I'm sure you will be able to come out with other similar operations and great algorithms you will build. I'll go back to the presentation. So these are all the references. This you have seen, of course, it's not really a reference, it's a tool, you can use it. And this is an ultimate reference. We have to thank IBM for giving us the quantum computer simulator, and then excellent documentation. Please go through that. And this is the paper which talks about quantum way of addition. Hope, I mean, they are the inventors for this. And this is an extremely good article written by this guy, Saswat. You love it. So, in fact, he has also given the QFT algorithm. So you can make use of that instead of IBM's if you want to. IBM. I mean, that will give a better understanding of QFT, what's happening. In fact, he has gone to such a level that he's explained what is Fourier transform and how it transforms the time domain data to frequency domain data. So it's an excellent article. Please go through that. And there's again a good YouTube like what I have given here. You can also go through that. And last but not the least, our great textbook, Quantum Computation and Quantum Information. So you can have that as a reference for understanding QFT. So that's all I have. What next? You can try it out, your own way of adding or multiplication or subtraction. Try to use different gates. We used CP gate. Instead you can use some other gates and then see whether you can get answer. I'm sure you can get it. And then what I'll do, I'll try to learn some more things and come back with more videos. Okay. Till then, bye. Thank you very much for seeing this video.